Hello there, welcome back to today's video. Now remember, make sure that you fully use your bubble pen, full explanation and full working out when necessary. So any question you got wrong, any question you got partly wrong, make sure you do those three things. Okay, alright, let's get started. Now what we have here is we have two slits. So this is double slit. Okay, so double slits experiment, and the waves are going through the slits. You can see here, so the waves coming through the slits. So one here and another one here, and then they meet up at this point at the detector, and the detector is detecting something. Okay, now I'll tell you here that the central position for the position of the central maximum is here. So this is the center one. Okay, so this is the first bright spot, or the first constructive interference. Okay, and then and so on and so forth. Now, what's meant by coherent source? Now, coherent source stands for two things. And the first one is the wave has to be monochromatic. Okay, so what is monochromatic? It means a wave that has the same. So waves, so both waves, they have the same wavelength. Okay, same wavelength, or they're going to have the same frequency. Okay, so that's what monochromatic means. Now, not only we have to use a wave that is monochromatic, the wave must also has a constant phase relation. Okay, constant phase difference. Yeah, so the word is difference, so the difference in phase between them must be constant. So these two waves, they must have a phase. They must have the same phase difference. The difference, phase difference, or phase relationship. Okay, so that's what you get for. So we've got one mark here and one mark for saying constant phase difference, because those two waves are coming out, the phase difference, the difference in phase between them must be the same. Okay, now this one should be straightforward. You know the equation, wave speed is equal to f lambda. Now the thing is, we're dealing with microwave, so this is light, so therefore c is equal to f lambda. You're looking for wavelength, you just rearrange your equation. Again, you plug your numbers in. Okay, now this one we need to convert the giga. The giga must be converted, so therefore it's going to be 9.4 times 10 to the power. So what is giga? Giga is to the power 9. Okay, so we need conversions, and then you get your answer to 3.2 times 10 to the power minus 2 here. So that is your answer. Okay, again, so for you to get your full mark, we must see the substitution with the conversions and then you answer in this particular case. Okay, now what's the phase difference between these, the path difference between the two waves? Now let's look at the waves. You got, so one wave here, 2, 3, 4, 5, and then 6. So here you have 6 wavelength, and here if you count 1, 2, 3, 4, 5. Okay, so from here to here that's 1, from here to here that's 2, from here to here 4, and then that's 5. So this is 5 wavelength. Okay, so therefore the path difference is equal to 6 lambda take away 5 lambda is equal to 1 lambda. Now lambda, we know what lambda is because lambda we already calculated it, isn't it? So we already calculated from here, so therefore I'll take it. So therefore lambda, so 1 lambda is 1 times power minus 2, okay, which is exactly the same, so 3 points. Here we go. So that is your wavelength in this particular case. All good? Now state, what do we get? So at this position here, so at this point where they're meeting, are we going to get a constructive interference or a destructive interference? Okay. Now what we're going to get is we're going to get a maximum. So first point, maximum. Okay. Now the question is, why do we get a maximum? Now maximum means it is a constructive interference. Now, why do we get a constructive interference? We get a constructive interference, okay, because the wave meets, because the wave, okay, because they have a path difference of 1 lambda. Okay, so that's what happens. That's why. So therefore they are in phase. So therefore they are in phase. Okay, so therefore when they meet with each other, so therefore when these two waves meet here at this point, they are constructively interfering at this particular point. That is why. That is why. Okay, first of all, you need to state. So we need to state. So we state. So it is a maximum. Why is maximum? So if it's a maximum, it means that we are getting constructive interference. Now, why are we getting constructive interference? Because of the path difference. Now, can I say something with phase? Yeah, I can say something phase, but the question is giving me the hint to use the path difference there. Okay, that's 3 marks. Good. Now this one you need to use the equation. So it's double. These are double slits, so therefore it's going to be the equation W is equal to n lambda capital D over S. Okay. Okay, 6 shows blah blah blah. Everything's given to you. Now we know that the central bright spot, so this is n is equal to 0, and then the second bright spot is going to be n is equal to 1. So therefore this is n is equal to 1, so therefore this will be equal to lambda D for S. Now we need to rearrange this. We're looking for the S, so S is equal to lambda D over W. Again, so the wavelength, which we know already, 3, 2, minus 2, bracket, times D. Now do we know D? The distance, where is it? Distance is 0.42 divided by the slit separation, the fringes separation is 0.11. Okay, now the answer is 0.218. Now the question wants me an appropriate SF. Now let me look at the question to know what is an appropriate SF. Now the question given me here, 1, 2, so this is 2 SF. The question here, 11, 1, 2, 2 SF, so therefore my answer was going to be 0.12, so therefore 2 SF is appropriate, because the questions are giving me the numbers to SF. Otherwise, if the question didn't ask me, we don't tend to care. Now, wave the detector at the position of the maximum. The frequency is double. State what would now be detected. So now we have, the detector is at the same place. Okay, so the detector is at the same place. But what we've done is we've doubled the frequency. Okay, now the first thing you want to ask yourself is the following. So frequency doubles. What happens to wavelength? Okay, now the wavelength, if the frequency doubles, the wavelength is going to half. Okay, now the speed of the microwave is still the same, because the speed goes at the speed of light. Okay, so you can't go faster than that. And so if the frequency doubles, then the wavelength goes down by 2, so therefore it halves. Okay, that's the first thing. Now, if the wavelength halves, what's going to happen to these guys here? What's going to happen to these guys here? Okay, what's going to happen to these guys? Okay, now think of this. If the frequency doubles, what happens to the number of waves? So if the frequency doubles, it means we're going to have more. We're going to have twice the waves. Twice the waves. In this case, what's going to have is, instead of having, how many waves do we have here? We've got 6 complete waves. So now we're going to have 12 complete waves. So we're going to have 12 complete waves. Therefore, 12 times the wavelength of the wave. So 12 waves. So instead of 6 wave originally, we multiply this by. We multiply the wavelength. We double the frequency. So number of waves passing a point per second is twice. So 12, and here we have 10. Okay, so we got 10 in this case, and then we have the difference is 2 parts. Therefore, this is the new path difference. Okay, now the path difference is still an integer lambda. Okay, so this is still integer lambda, so in bracket and lambda. So this tells me that I'm gonna get, so what I'm gonna get, I'm gonna get a maximum, which is a constructive interference. So it means that interference, it means that even though the frequency doubles, I'm still gonna get a constructive interference at this same position. Okay, all right. So now, if I have to draw it, let me just draw it so that you understand what's happening. Is I got the 2 slits here, 1, 2 slits, 1 slit, 2 slits. We have the central one here, and then we have the detector here. Okay, so this is the detector. Now, what's happening is we're doubling the frequency, so the number of waves coming is double. So here we got 12, and here we got 10. Okay, now since the path difference is 2 lambda, which is still an integer, so you can remember, so for us to get constructive interference, it could be 1 lambda, it could be 2 lambda, 3 lambda, so integer lambda in this case, yeah? Okay, 1 lambda, 2 lambda, and so on, yeah? So therefore, the wave will still meet here in phase. So therefore, we get a constructive interference on this particular point. Good. Now let's move to the next question. Okay, so this is a question where we need to be careful with. Okay, so air, so this is glass. Now we know about something here. We know, does it tell us something? The medium refraction is, medium 1 is, okay, so this is less dense. It's denser. Okay, now the first thing we need to do is we need to draw the normal. So we always draw the normal. So the normal, so this is the boundary, okay, and the normal will be perpendicular to this here. So I'm going to draw it perpendicular. Okay, so this is perpendicular. Again, let me just zoom in so you can see. Again, so this is roughly perpendicular. Okay, perpendicular as you can see here. Okay, now the first question says, without any calculation, sketch the refracted path. Okay, what's going to happen? Okay, so now since the wave is entering a denser medium, it's gonna, what's going to happen? It's going to bend. It's going to bend where? It's going to bend towards the normal. So therefore, the wave is going to look like this. Okay, again, let me just change the color for this one. So I'm going to use a color red, so it's going to bend towards the normal. That's not good enough. That's not good enough. So it's going to bend toward the normal. Oops. Okay, let me just, yeah. Bend toward the normal. Let me just do this again. Okay, here we go. I'm going to use the red one again. It's going to bend toward the normal. Here we go. Okay, so as you can see, it's bending towards the normal. Yeah, it is not on the normal, it is towards the normal, close to the normal. Yes, bend towards the normal. Good. Now, what else? So emerges into the air. So it emerges into the air. Okay. Okay. Now, air we know is less dense. So therefore, here we must draw the normal again. So normal will be perpendicular. Again, so use a ruler, it must be perpendicular. Now, where will it bend? It's going to bends away from normal. Therefore, again, I'm going to use the red color. So therefore, it's going to bend away from the normal. So you can see here. So see, it's bend away. So here, it bends towards. Good. So there's 2 marks there. Now here it is reflected. We need to draw this reflected into the same medium. Okay. Now it is so whenever something is reflected at this angle here, I'll call it I. must be the same as the other angle. Okay, so therefore it's going to be something like this. Okay, oh, okay, it's the same angle. Okay, so angle of reflection same as angle of incidence, which is I here. Let me put a bracket I. Oh, here. Okay. Now what else do we need to know? And then we need to draw when it's emerging into the air. Okay. Now same thing is merging into the air. We need to draw a normal here. Dot 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 dot. And what happened in this case? Okay. So what happened in this case? Where it's going? So it's going out. So therefore it's going to bend away from the normal. Okay. Again. So away from normal. Now how do I know it's going to bend away from the normal? I know because the refractive index of medium 1 is 1.4, so this is 1.4. Okay, medium 2 is what is it? Medium 2 is 1.6. Medium 2 is 1.6. Okay, so we got medium 2, which is denser, and then followed by medium 1, and then air. We know that the refractive index of air is 1. Okay, so air is lesser denser, less denser, yeah, lesser denser. I don't know what's the word you want to say. So therefore it bends away. Again, use a ruler. So I don't have a ruler here. So use ruler. Okay, plus draw normal. Okay, so be very careful where it's bending and so on. Yeah, good. Okay, now give the angles of incidence. So we're looking for the angle of incidence. We want to find this angle here. What is this angle here? Okay, now let's take a look at this one here. Okay, I'm going to use a different color pen for that. Let's use a green. Okay, now we know that this is 90 degrees. This is 90 degrees. Okay, so this is 70. So therefore this here would be 20 degrees. Okay, so let's zoom in now. So this here will be 20 degrees. Let's zoom in. So this here will be 20 degrees. Okay, let's zoom in again. Okay, so now we are left with this here. So what we know is we know that this is 90. So if this here is 20, so therefore this here will be 70 degrees. Okay, okay. Now, if this is 70 degrees, this here, so this here, if you can see my cursor, so the 70 degrees and the angle of incidence is actually 90 degrees. Okay, so this is actually 90 degrees there. So if I have to draw it, let me just put it into one side. So it's going to be like this. So you've got 70 degrees. Got 70 degrees here. And then this is the normal. Okay, and this is the normal. So we know that the normal is 90 degrees. So therefore I, what will be I? So I will be 90, take away 70, this will be 20 degrees. Okay, and that is the answer in this case. Again, if you've got anything wrong, make sure that you do pop up on your work. You see I've added the explanation there as well. Make sure that you also add the explanation as well. Okay, now this is Snell's law. Okay, now medium 1 we know 1.4. Sine now we know is 20 degrees. It's equal to medium 2 1.6, which we know. Sine this we don't know again, so you can see equation, substitution, and then you rearrange. You rearrange the equation. Okay, I rearrange my equation. Sine inverse, theta 2, rearrange, and then finally your answer with the units. So this will give me 17.4 degrees, okay, or 17 point something degrees, yeah, and this will give you your marks there. Okay, all good, excellent. All right, let's move on now. Calculate the critical angle of air. So critical angle we know again, so do the same equation. Okay, now so let's have a look. The critical angle is the angle of incidence when the refracted angle, when the refracted angle, which is theta 2, is at 90 degrees. Okay, so therefore I'm going to rewrite it as sine 1, sorry, n1 is equal to sine theta c, c for critical angle is equal to n2 sine 90 degrees, because this is what the critical angle is. The critical angle is the angle of incidence when the refracted angle is at 90 degrees. So therefore, I'm going to have sine 90 is just 1. You guys know this already. And then rearrange for sine critical angle. Okay. And then sine inverse n2 over n1. Okay. And again, now n2 you know is 1 point. So let's have a look where are we going. So we're going from medium, so we're going from medium 2, so therefore n1 will be medium 2, and air will be n2, so therefore so therefore medium air is 1 divided by n2, 1.6, and this will give me 38.7 degrees. Again, so I need to see your points, because this is just 2 marks there. So I need to see that you've done, I can see that you've recognized 1, and then the other one goes away because sine 90 is 1. Okay, good. Let's keep going. Okay, now this is 1 mark, 1 easy mark. Okay, so this one almost, we've got this correct. So what is it? What is nuclear number? It's the number of protons and neutrons. Okay, what is this? Proton number. Proton number is the number of protons. Okay, so this is straightforward, 1 mark. Okay, now calculate the number of neutrons in this one. Okay, now nuclear number is 14, so therefore in the nucleus there's 14. Okay, so therefore it's going to be 14 take away proton number. So as you guys know, okay, so we've got proton plus neutrons is equal to 14. So therefore we need to take away proton from it. So therefore 14 take away 6 give us 8. So the answer is 8. Now specific charge is charge over the mass. Now the charge comes from the protons, therefore 6 times the charge. Okay, so 6 times power 19 divided by the mass, that's from the nuclear number, times 1.67 power minus 27. Okay, so again the charge comes from the proton, so therefore 6 times the charge. Okay, and then the mass of the nucleus come from the nuclear number, which is the nucleus, 14 times the mass of the nucleon itself, and this will give you 4.1 times 10 to the power 7 in this case. Again, it's 3 marks, so I need to see substitution, and the final answer over there. Now, what is meant by isotope of same, pretty much. Okay, so there are variations of elements with same. So what's the same? Same proton number, but different nucleus, neutron number, okay, so they have the same proton number but different nucleus number, neutron number. So therefore, how can you work this out? Okay, so therefore we need to use the charge. So specific charge is equal to charge over the mass. Okay, now we know that the charge is from the nucleus, and we know that this is an isotope, so the nucleus will have the same proton number, so 6 times the charge of there, 6 times 1.6 times 10 to the power minus 9 divided by the mass. Now, do we know how many nucleus do we have in the nucleus? We don't know, so I'll call this call this nucleon number. I call this let's say I'll call this capital N times 1.7 power 7. Okay, and all we have to do now is we have to rearrange this in this particular case. So therefore I'm looking for N. Okay, so therefore N go to 6 times minus 19 divided by specific charge. We know specific charge is 4.8 power 7, so therefore 4.8 power 7 multiplied by, okay, so this is my substitution, and then this will give me an answer of 12. So therefore N is equal to proton plus neutron is equal to 12 is equal to proton, which I know 6 plus 1, so therefore 12 take away 6 is equal to N, so 6 is the answer. Again, it's 3 marks, so what we need to see is I need to see the first step, the second step to show that you got 12, and the last step to get 6. Okay, and that was the last question. Here we have a fluorescent tube in this particular case. Excited, what happened in this particular case? Okay, they emit photons. Okay, now let's have a look. So if you remember, when we draw the tube, we've got the coating, because this is a fluorescent tube. Okay, now the tube has atoms in it, mercury atoms with the shells. Okay, you've got a piece of metal here, it's connected somewhere. Now what happened is you have electrons coming from the wires, and those electrons, they are at high voltage, so therefore they are able to accelerate at high speed. Okay, and these electrons will collide with the electrons. Let me just use a difficult pen so you're not confused. Red. Okay, so this guy will collide. So this guy will collide with the electrons inside the atoms, and this will cause the electrons in the atoms to move up energy levels. And then once moved up, what's going to happen is it is excited, and then it wants to de-excite. So when de-excite goes down, and this will emit a photon. Now, since this is mercury atoms, since the electrons here has high voltage, therefore high energy, so therefore the photon being emitted will have high energy photons. So therefore the light that is emitted would be ultraviolet. Okay, ultraviolet. Now, what is meant when it is excited? So what does it mean it is excited? So when it is excited, remember, so all we're talking about is the electrons, okay, has moved up, energy level has moved up, energy levels. Okay, let's move up to higher energy levels. Yeah, so the electrons, remember, if I draw the nucleus there, we got the shells, blah, blah, blah. So if there's electrons here, let me use a pen here, so electrons here. So when it gets excited, it means that this electron has moved up to a higher energy level. Okay, again, so it wasn't, yeah. So that's all we have to say. Electrons move up. Now, how do the mercury atoms become excited in the first group? Become excited. Now, first of all, how does it get excited? So for it to get excited, what happened is electrons. Okay, so we've got these electrons here in the wire. Okay, so 3 electrons. Okay. So 3 electrons at high voltage. Are accelerated. Okay, accelerated, and what do? Is they collide. They collide with electrons in the atoms. Okay, and when this happens, that's how it's transferring its energy. It's transferring energy through collisions. Again, if you got this wrong, if you make sure that you have these 3 points there. Well, it should be 2 points, but I've split the last point here. Okay. Now, why do the excited emit specific frequencies? Okay. So why do they emit specific frequencies? Now let's look at the atoms again. So here we go. Okay. Now let's try to understand this. Now the electrons. So this is the ground state. Okay, so this is 2, 3, 4, 5. Now the electrons, they can only exist, they can only stay at those particular levels. Yeah, so they can be here, they can be in the second one, third, fourth, fifth. They can't be in between. They cannot be in between. Okay. Now the first point we're going to say. Okay. So how do they emit? So first of all, we're going to say. Okay. Electrons electrons can only exist at discrete energy level in the atom. Okay, so in the atom, they can only exist at discrete energy levels. They can't be in between. Okay. Now here, since we're talking about emitting photons, so it means that this electron here has already gone up. Gone up. Okay, so this electron here has already gone up. So let's say it's gone all the way to the fourth one here. Yeah. Okay. Now here we go. So when the electrons, okay, so when electrons de-excite, so they are, what happened? When they're changing energy levels, when they're dropping down the energy level, okay, they excite to a lower energy level, okay, they must lose. So for them to de-excite, let's say they have to de-excite, in this case, let's say they have to de-excite down to, let's say, this one here, they must lose I would say a specific amount of energy corresponding so they de-excite to a lower energy level, so they must lose a specific amount of energy dependent on level change, I would say. Okay, so that's why you have this, for example. So in my example here, the electron has dropped down from N4 to N2. So therefore, it's going to be the energy level at 4 minus the energy level at 2, and this here will be the energy of the photon being emitted in this case. Okay, the energy in this case. Okay, and it must lose exactly the same energy. Okay, so that amount lost, that amount of energy lost, okay, will lead to a specific photon with specific frequency. Okay, now, so if the difference is more, therefore the energy, the loss will be more, so therefore this photon will have that amount of frequency, so therefore this particular color. Okay, good. Again, so 1, 2, that will be the last point. Good. Okay, so this one here we're looking for frequency, so we got energy equal to this. The wavelength we know. Okay, mercury atom is nanometers. Do we know anything else? Okay, blah 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 blah. Yeah, we know, so we don't need this one here for now. So this is for later. So we need. Okay, so frequency is equal to speed of light over this. So this one's straightforward. Speed of light, you guys know this already from the formula sheet. Nanometers must be converted. Okay, so this is power minus 9. This will give me 1.18 power 15 hertz. Okay, now electron volts again, so energy is equal to HF. Put the numbers in, multiply by the frequency that will be calculated already, and this will give me an answer in joules. Okay, now we need to convert this into EV. Now what we know is we know that so 1 EV is equal to joules. So therefore I'm looking for this in joules, so therefore it's going to be divided. I need to divide it by 1.6 power 19, and this will give me an answer of 7. So this is what I need to do. I need to divide. Some people forgot to divide. Okay, good. Now, how the coating inside emits visible light. Now, in this case, we got the coating here. Okay. Now, when the UV, so what's going to happen? The UV is emitted from the atoms. The UV would be absorbed. So UV, the UV, ultraviolet light, gets absorbed by the coating. Okay, and then what's going to happen is same thing is going to happen. So you're going to have excitation. So the electrons inside the coating, so the electrons inside the coating will get excited to a higher energy level, and then they're going to get de-excited to a lower energy level, and this will emit a visible light. Now what we'll do is in bracket I'm going to have so excitation plus de-excitation. Okay, and what's going to happen is this will lead to, okay, so photons with low frequency being emitted. There we go. Okay, now the question tells us it is emitting visible light. Now visible light has a lower frequency compared to UV light. Visible light has a lower frequency compared to UV light. Visible light has a longer wavelength compared to UV light. So we need to say that the photon being emitted, yes, we know it's visible, but what is it that makes it visible? It is the lower frequency. Okay, so therefore it has a lower energy. It means when it goes up, it only went to a and then dropped down, so the difference was small. Okay, good. Now this one here. Okay, so you guys should be able to do this. Okay, microphone is used to direct the wavelength of this. So we've got this one direct. This is this one, and what's going to happen? Okay, now we know it is metal plate y-axis, blah blah blah. Midpoint with point here. Shown below. Which one is incorrect? Which one is not correct? So which one is incorrect? Pretty much. Now, if we have a wavelength of 30 centimeters, it means that the wave is going to be something like this. Okay. And what happened here is going to reflect on itself. Okay. So this is 30 meters. And what we have is we have here destructive interference. And here we have constructive interference. So this is a standing wave, yeah? So this is a standing wave. Now remember when we did this with the rope, yeah? So this is the constructive interference. It goes up and down. They meet up here constructively, destructively. Okay. Now, the two distance between minima could be 15. So let's take a look. So 15. So from here to here is 15. Okay, the distance between two minima means destructive interference. So this here is a destructive interference. Okay, so this is correct. The distance between two maxima would be 30. So from one peak to the next peak, so two maxima. So this would be a maxima, and the next maxima would be, so from peak to peak. So from peak to peak, if I continue the peak. Okay, so this would be one peak there, and the other peak will be there, so it'll be 30 degrees, so that's correct. Okay. Okay, so this is the peak for the peak. This is the bottom peak with that. The distance between one minimum, the eye, and this is 30 millimeters. Clearly, the distance from one minima to the next maxima is not this. From this to this be 37. So this is 50. This is 50, 30, and then this one's correct. So therefore, the answer is going to be C in this particular case. Okay, so you can clearly see that the distance from one maxima and minima is not 30 millimeters. Okay. Now this has to do with the equation. Straightforward. Okay, so which line in the table will give the change that will increase this one here? Okay, so you're increasing the spacing of the fringe. Okay, so fringe separation goes high. Okay, as it goes high, what's going to happen? So let's take a look. The distance from the slit, if this goes up, the distance of the slit is going to increase. Okay, so therefore you're left with two options, so B and D. Okay, and the slit separation has to go down, so therefore it's going to be B in this particular case. Again, you can see that W goes up, S goes down, so it's half, and then if W goes up, D goes up, so therefore it's going to be this one here. Okay, and the last one, this one's straightforward. Okay, so you guys know how to convert this by now. Okay, so 0.41 radian divided by pi times 180 degrees. You got this one, and the answer is this one here. Okay, so all done. Again, make sure that anything you go wrong, you got the explanation there. You can see the explanation there. You can see the diagrams there. You can see the whole diagrams there. Everything's there. Make sure that everything is in your book, well, in your paper in this case. Okay, crack on.